This is a discussion on the fundamental theorem of algebra. Now, I'm not going to come out and tell you what the fundamental theorem of algebra is right away. We are going to discuss some possibilities and then see if we can discover something that these quadratics have in common. So first thing, if I look at this quadratic and I solve it with the quadratic formula, my a is 1, my b is -5, and my c is 6. I go to plug it in my quadratic formula of -b plus or minus b squared minus 4ac all over 2a. I always use parentheses when plugging into the quadratic formula to help me keep track of my negatives. And so I get positive 5 plus or minus the square root of 25 minus 24 over 2. And so I get 5 plus or minus, that's the square root of 1. But the square root of 1 is 1. So at this point, the plus or minus means I'm going to get two solutions. So I need to break this apart and solve for two solutions. So I get 5 plus 1 over 2, and I get 5 subtract 1 over 2. 5 plus 1 is 6. 6 divided by 2 is 3. 5 minus 1 is 4. 4 over 2 is 2. So these are my solutions to my quadratic. But what are solutions to a quadratic? We're going to go ahead and take a look at the graph of this quadratic. So I'm going to use Desmos to just graph it so we can see how these numbers might relate to the picture. So I have f of x is x squared minus 5x plus 6. All right, so let's check. So x squared minus 5x plus 6. And this is what the graph looks like. I'm going to go ahead and zoom in on the x-axis. And as I zoom in, I want you to notice that where it's touching the x-axis is 2 and 3. So what was my solution? My solution was 2 and 3. And where did it touch that x-axis? It touched it at 2 and 3. So 2 and 3 are my solutions to my quadratic, but they are also the zeros, the intercepts of my quadratic. And we also refer to these as the roots of our quadratic. So, to tie it in, I could rewrite this in factored form. And in factored form, it would be x minus my root, x minus my root. X minus where it touches the x-axis. So where does it touch it? At 3. Where does it touch it? At 2. Which, looking back, there's x squared minus 2x minus 3x, which makes negative 5x together. And then negative 3 times negative 2 is positive 6. So there's my factored form. And notice when I plug in the zeros, 3 minus 3 is 0. When I plug in the solution, 2 minus 2 is 0. Alright? So notice I ended up with two solutions. Okay? And these solutions are real numbers. They are real numbers. Now let's take a look at f of x equals x squared minus 4. So on this one, my a is 1. I don't have a linear x term, so my b is 0, and then my c is -4. So I'm going to get x equals -b plus or minus square root b squared minus 4ac all over 2a. And so my b is 0, my a is 1, and my c is -4. I'm going to get 0 plus or minus the square root. Well, 0 squared is 0, and so that's the square root of 16 all over 2. So I'm left with plus or minus, the square root of 16 is 4 over 2. I can now break this into my two equations. So I get positive 4 over 2, and I get -4 over 2. 4 over 2 is 2. Negative 4 over 2 is -2. So now let's look at what the graph is. Let's look at its graph. X squared minus 4. I need to zoom out this time. And as I look at the x-axis, notice, where is it touching the x-axis? 2 and negative 2. 2 and negative 2. So I can rewrite this in factor form by doing x minus and x minus. And you put in that solution value. So I'm going to take this positive 2 and plug it in right there. I'm going to take this negative 2 and I'm going to plug it in. So that tells me where my zeros are. These solutions are my zeros. And notice I'm getting 2 real answers again. I'm getting 2 real answers. So I have x minus 2 and I'm getting x plus 2. Alright, let's look at our next one. X squared plus 4. X squared plus 4. So my a is 1. I don't have a linear term again, so my b is 0, and my c is 4. So if I get x equals negative b plus or minus the square root, b squared minus 4ac all over 2a. Plug in my b, my a, and my c. And this time I get 0 plus or minus the square root. And this time when you multiply under the square root, that's a negative 16. Well, remember, negative numbers, the square root of negative 1 is I. So this becomes plus or minus I, the square root of 16 over 2. Well, the square root of 16 is 4, so this is positive I, positive 4I over 2. That's positive 4I over 2, and it's negative 4I over 2. 4I over 2 is 2I. Negative 4I over 2 is negative 2I. So notice these are not real anymore. These are not real. So let's take a look at its graph and see why we are getting non-real solutions. So let me change this to a plus and let's see why we are now getting non-real solutions. I have to zoom out a bit here. Alright. Here's our new graph. Here's our new graph. So notice the graph is shifted up this time, and it's being shifted up. So it's actually 8 up from the previous one. And notice this time it no longer crosses the x-axis. It is 8 up from the previous graph. It no longer crosses the x-axis. Alright? And so since it's no longer crossing the x-axis, we now have these non-real roots. All real roots will fall on the x-axis. But there are still 2 solutions. So I'm still getting 2 solutions. So I could rewrite this in factor form with these solutions. Even though they're not real, I could still write it in factored form. And so what my factored form is going to look like, each time it was x minus your root and x minus your root. So this time my root is 2i and negative 2i. So this comes out to be x minus 2i and x plus 2i. And there's my factored form of x squared plus 4. It does not have real factors, it has non-real factors. Now notice all 3 of these quadratics had 2 solutions that were complex numbers. Let's look back at the original. How is this a complex number? It's a complex number because it's 3 plus 0 imaginary portion. 0 non-real portion. 2 plus 0 non-real portion. So it is a complex number. Remember, all real numbers are complex. This is a complex number because it's 2 plus 0i. It's negative 2 plus 0i. So they are complex numbers. And this one is a complex number because it's 0 plus 2i. It has 0 real component plus 2 imaginary, 2 non-real. Remember, imaginary and non-real kind of go hand in hand with each other. So that's 0 minus 2i. To check that this factor form is correct, let's go ahead and actually distribute it out and see if we get back to x squared plus 4. So let's see if this rule applies that our solutions I can plug in as x minus the root. Let's see if this works. So I'm going to go ahead and distribute this out and simplify it and see if I get back to x squared plus 4. Alright, so I take the first term and I distribute it, and I get x times x is x squared. I take my x and I distribute it, and x times 2i is positive 2xi. Then I go to my second term, negative 2i, and I distribute it, and negative 2i times x is negative 2xi. And then I distribute it again, and negative times a positive is a negative. 2 times 2 is 4. I times I is I squared. But remember, so first thing, those cancel. Okay, plus and minus of the same amount, they cancel. But remember, this I squared is really negative 1, because the square of the square root of negative 1 is just negative 1. So 2 negatives become a positive. So basically what the fundamental theorem of calculus tells us, is that my exponent up there tells me how many roots I will get. It does not necessarily tell me that they will all be real roots, but I will have 2 roots. So here I had 2 imaginary roots. The previous one I had 2 real roots, and the one before that I had 2 real roots. So the degree of your polynomial, the greatest power on your polynomial, that will be how many roots you can have. And they will all be complex roots, but they may be real or non-real, or a mix of both, okay? So it can be either. So that's it for the fundamental theorem of calculus for today. Fundamental theorem of algebra for today.